At noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Let's draw a diagram to help us figure this out. So we have two ships, A and B, which I'll label with these two dots here. So ship A is 100 kilometers to the west of ship B. So I'll call this A, I'll call this B. And then we have this distance here, and this is 100 kilometers. Now, ship A is sailing south at 35 kilometers per hour, which is a faster rate than ship B. And ship B is sailing north at 25 kilometers per hour. If we want the distance between them, that's going to be the line that goes from here to here. So I'll draw it like this. What we want to know is, how fast is this line changing? In fact, how fast is it increasing? What we're going to need is, well, first of all, some variables that I'm going to label in this picture, and then we'll attach it to, well, the numbers that appear within this question. So for starters, I know this line is increasing, therefore it's a variable. I think I'll label it x. And this line is increasing as well, so I need a different variable for it. I'll call it y. And, well, this is a line that connects to two ships, so I'll give that another variable, which I'll call z. In terms of what we're solving for in this question, we're looking for the rate at which z is changing. Like, this is the thing we want to know. Now, we should be able to know what the rates of x and y are, and those are given within the problem. If ship A is moving in this direction at 35 kilometers per hour, well, that is dx dt, the rate at which this side is increasing. Since it's increasing, it is a positive number, and it's going to be positive 35, and that's kilometers per hour. This side is increasing as well, so I know it's a positive rate, and that rate is 25 kilometers per hour. So now that we have variables, we have the derivatives, and we want to solve for this thing here, I have to somehow connect x, y, and z in an equation. And I think the way you can do this is by drawing a triangle in this diagram, a right triangle. This triangle here. In this right triangle, we can square this side, add it to the square of this side, and it's equal to the square of this side. That is something we can take the derivative of and hopefully connect the rates of x, y, and z together. Well, I know what the length of this side is. It's fixed. It's always equal to the length of this side, which is 100. So I'm going to start by writing down, well, that's 100 squared plus, all right, what is the length of this side? Well, it's equal to x plus y. And then you have to square that thing. This is equal to the hypotenuse, which is z squared. Okay, great. Here's an equation that connects x, y, and z. I'm now going to differentiate both sides with respect to d. The derivative of 100 squared is 0. I'm not going to write it down. The derivative here of x plus y squared is, bring down the 2, copy down the x plus y. You subtract 1 from the exponent, which I won't write, but you have to multiply by the derivative of what's in the parentheses. That is dx dt plus dy dt. And on the other side of my equation, the derivative of z squared is 2z dz dt. We can simplify this a little bit. I know I can cancel those 2's. Those are unnecessary. And, oh, I can also divide z to this side of the equation, leaving me with dz dt by itself. I mean, ultimately, this is the thing that we're looking to solve for, so I'm going to isolate it. I'm going to reverse the direction on it. I'm going to say, well, dz dt is equal to this whole side divided by z, and I'll just put z in the denominator here. So that is, we get x plus y over z. I don't really need parentheses on that numerator anymore. And then I have dx dt plus dy dt. All right, we're basically, well, I mean, we're close. We're really close. What do I know down here? I know dx dt, and I know dy dt. Unfortunately, I really don't know x, y, or z. I don't know any of those things. There must be something in the question that can tell me this. Here it is. We know the rates of both A and B, and we know how long they've been traveling. If you start at noon and you end at 4, that's 4 hours later. So it's kind of hidden, but t is equal to 4. We're asking, how is this line changing at 4 hours, which is 4 p.m.? I can multiply this t by the rate to determine the length of x and the length of y. That makes sense. If ship A is going 35 kilometers per hour, and I multiply that by 4 hours, that's going to be the value. That's going to give me the value for x. So that is x is equal to 35 times 4, and y is equal to 25 times 4. So y is really 100, and x is equal to 140. Okay, so I now have x, I have y, but I still don't know z. But we have this equation over here, and we can put x and y into it to solve for z. So let's do that next. Kind of running out of room, I'm going to put that here. So let's see, that is 100 squared plus, okay, then we have 140 plus 100 squared. That's equal to z squared, which means I'll take the square root of both sides to solve for z. So I put this information in here, and I'm solving for z by taking the square root of both sides. I'm just going to get this value from my calculator. So let's see. If I take the square root of 100 squared plus 140 plus 100 squared, oh, it actually works out nice. The number I got was 260. That's the value of z. I think we can plug everything in to this formula now. Let's do it. dz dt is equal to, okay, that's 140 plus 100 all over 260 multiplied by 35 plus 25. Again, I'm just going to do this in my calculator to get a value for it. So let's see what we have. 140 plus 100 all divided by 260. And then that whole thing multiplied by 35 plus 25. And the answer I got, I mean, it's a decimal. I think maybe I'll just round it to one decimal place. This is 55.4. That is the rate at which this side is increasing. And so those units would have to be kilometers per hour. And this is the answer to the question.